Good afternoon. Thank you for the participation. And as a subtopic, I will talk a little bit about the innovative technology. And actually, in the morning, a lot of things got already mentioned. I will elaborate on some of the detail. So in the morning, TPDR was already mentioned, and I will talk a little bit about that as well. The reason is that for an architecture is no longer fixed forever, so we are always evolving them according to the technical demand. So the key is that we are looking at the balance between the performance and power. So why do we think like that? Because when we are facing the problems on the right side target markets, like for the cell phone or the automotive industry, we are paying attention to that. But now we also are faced with the servers and data centers and those demands. So for a cell phone, I think you all know that the balance between performance and power is of top concern because it's driven by battery. But now for the automotive, it's the same thing because automotives are getting smarter and more electrified. So for the backing the car or running the car, the performance requirement is really high, and radiation also needs to be taken care of. And for data centers, actually, the demand is getting clearer because in a space, how much computing power you can incorporate is really important. So the performance and power can decide how much computing power you can put in a certain amount of space. So that decides your other things like the radiation. So we do have the motivation in the market. So for the driving forces in the market, it was already mentioned in the morning by Dr. Shi. So when faced with many markets, the scalability requirement is really high. So we are also thinking about this. For example, in the past we need just a small mouse, but in the future we need an elephant. So we are thinking about the triplet technology to satisfy the cross discipline support. And then for FUSA, it requires a lot of safety redundancy. A lot of things must be calculated twice, and we need to think about the fail-safe issues. And packaging technology and power and the temperature are really important. So when we do the design of IP, we cannot just stop at the current level. So when we think about the things, thermal control is really important, and also the bandwidth limitation. This is also important. So for bandwidth, maybe you can use DDR or some other things, but we need to think about the efficiency of the use of memory. So we are trying to integrate on-chip memory. We are thinking about the chiplet-to-chiplet communication, and if we make things smaller, then we may make things better. And then finally, security. So now for the individual data or the enterprise data is stored on the cloud. So for the GPU, it's just one link of the safety chain. If we can make sure that the data is safe and the private data will not get leaked or stolen, then of course it helps, and this is one of our considerations. And we will elaborate on the four areas. So first, let's take a look at the scalability. So if we take a look at the C series, the CXT for 481 or for the 15 for the 16512, that means it's 512 flops. And of course, we can multiply that and we can form a single core, but single core doesn't satisfy, so we definitely need to do some other things like MC2 or 3 or 4 to have like 4 or 8 cores.
But even that, it still may not be enough, and you may need multi-instance with several CPU, GPUs put together. So around that, we need to do some further things with driver. For example, make it supporting 8K core or multi-instance. so that we can make that shift from mobile to cloud to other terminals. So these are the issues we've been thinking about and how we address the scalability and how do we design those hardware. And when we were doing the designs, we would consider those on-chip network technologies. And a single multi-core is actually a structure of it, as you can see here. And we do that chiplet design very much in accordance with this design. And now with a lot of hardware virtualizations, so one device may be able to drive 8 virtualized devices. And also on automotive applications, you need to have redundancy. If one device is broken or one core is failing, the other things should be able to compensate for us. And there are many other heterostructural, heterogeneous designs as well. So we do not wish to go towards the traditional way of designing it with a complex central block, because that means we have to do the redesigning of that central block all the time. This is not compatible with the chiplets designing principle. We do not want it to have a very large core GPU. Instead of that, we want more flexibility with it and using technology such as chiplets to increase its scalability. And speaking of scalability, I also need to mention the tile-based technology again. We have been hearing this word again and again today, but it's been evolving. The first thing is that the tile-based blocked bit rendering, it helps to reduce the consumption of bandwidth because it stays on that chip and finishes itself within chip memory. And between different tiles, you can write them out with a sort of burst, and then the cache and the fetch, everything would be easier with Khronos APIs, and you don't have to write all of those memories. And another thing you probably haven't noticed, when doing TB tile-based rendering, it also helps with scalability because the tiles are independent tasks. It means that we can easily allocate these different tiles and the tasks. And it gives us better linear scaling performance. So traditionally, it's between different chips, it's difficult to distribute that to multiple cores, but with tile-based, it's much easier. And we've been also considering how to make tile-based rendering even better. For example, the tiling is not simple to put them into different tiles. But we need to do a more perfect tiling, just like I have illustrated here. There are different ways of tiling the same picture here, and the better way to do it will allow you to reduce the workload and consumption. If you do it perfectly, you can save up to 50% of the computing consumption. So you can see the one on the left represents the perfect tiling. And in each tile, the load must be fixed as well because your chip's performance limit threshold is there. For those things that we traditionally aren't able to see, the triangles, etc., we can call away those tiny triangles. And for the other things, such as the small object culling, depth-based culling, these things are what can be eliminated. And we have a lot of patents technology on this. And also, even for each tile, we could do the compression, be it geometry or flops compression. And later, I will mention more about compression. And for each tile, there are quite a lot of things to further innovate, and we are working on that as well. With this slide, it's also mentioned by Ning Fei from Oppo in the morning. And after tiling, what we need to do along this streamline is that we need to have that preliminary list and the vertex data to express the list really clearly, which triangle in which tile, and within this tile, what are the triangles that are included. This is the part where that has to be expressed. And afterwards, everything is more independent on each tile. And we can use the on-chip memory to do the HSR processing, like what should not be able to seen and cannot and doesn't need to be rendered and buffered, etc. So with this architecture, we now also face some challenges in multi-core scenarios. The primitive list, after it is written, it can be independently processed and rendered, and it supports multi-core. But for TA, the geometry part, we actually are having some changes. We have an internal AGP function, advanced geometry processing feature. Once you toggle that feature on, that means this part could also be distributed to multiple cores. So for the renders, the two parts are actually going on in parallel, and the rest of things on this slide would be much easier to be processed. So that is to say, we are making innovations to that. And you can see that on the upper layer, the on-chip, well, there aren't much data to process, but at the lower level, we have for buffer, for primitive data, geometry data, texture data, and a frame buffer. And actually, we can compress all these four buffer area data. ASTC, ETC, and ETC2, we can use the Khronos standard to compress it. For the texture, when you are developing your application, you can use this high standard compressed format to express the texture. And for the rendering part, we have IMGIC, which is the image compression render. It can help to compress the image. Even if with display, you can compress that display if your displayer can support that. And the third part of it is PVRGC, which compresses geometry data. Now, the compression technology covered almost all data related to rendering. So be it on a buffer or HDR or render targets, and the performance with those compression you can see on our results when compared with Manhattan or Aztec or PUBG low or high quality, you can have 20 to 40% of widthband saving, and that saved widthband actually can help your products to have much better consumption capabilities or even longer battery life, etc. It also helps them to increase the performance as well. So the TBDR architecture has been evolving according to the market needs we see there. And here I also would like to mention about safety. With safety, I'd like to mention two examples. One is the virtualization related or simulation related safety. Well, this is often used in automotive testing scenarios because now in vehicles there are multiple screens for the entertainment system, the navigation systems, etc. And that means you need to have a load allocation, or how much load you're going to offer for that, for game, for entertainment, but what should be reserved for driving, etc. And now with our architecture, we can have that very dynamic and GUI responsiveness with performance budget of workload allocations, and we can do that. Later, I will elaborate more on how. And on the right side, you can see the security and isolation of workloads. The different OS, they have different purposes. Some are only for entertainment, some are for navigation, and some are even more important in driving when it comes to safety. So it must be isolated. As you can see on the right side, you see some errors there on navigation. You can restart the system without actually affecting the dashboard of the vehicle. So this is how the dashboard had been isolated. And this is not only about GPU, but we can use it to enable together with the AI and the GFX and allocate the GPU computation powers, etc. And now I also would like to mention how we actually do those improvements. For example, virtualization. And efficiencies of GPUs actually based upon our firmware. That firmware is programmable. And with that programmability, it helps the main CPU to reduce the workloads. Because when doing the rendering, a lot of interruptive signals doesn't have to actually go back to the main CPU core, while the smaller cores could deal with it. And also, as I said, with virtualization and isolation in those scenarios, we can even assign that for a specific SC. And in the future, if you have other new requirements and cases, you can easily adjust that within this firmware, such as what we are doing now with FUSA to be used in automotive industry. It's programmable and scalable. The scalability also allows you to do better debugging. Like in the morning, we heard that in full time, the debugging, the flush for the GPU was pretty difficult. But now with this firmware, it can have a log generated for you. You can to do GDB, debug, or step-by-step mode, etc. Well, crushing, when crushing happens, it's not entirely our responsibility. We can use those logs to tell you what could be the root cause for that and help you to identify the problem. And with this firmware, another great advantage is that it knows what's the data inside the GPU. The domain control and the working loading systems and the information, which allows you to have better connections with the outside. For example, with the GPIO interface, we can use that to communicate with the CPU. Like if the frequency is too high, temperature too high, or if you are needing 1 millisecond to respond, should you be able to adjust that, etc. There are smarter control that can be achieved with this. So previously, I have just talked about those challenges we face in the market from mobile efficiency and the scalability further towards desktop and cloud, the physical design and packaging awareness, as well as the wider range of markets we're targeting at, as well as the scalability and the safety, that we are all making these improvements according to what the market needs. And we have over 25 years of GPU leadership, and ray tracing is also a technology that we've been improving. The tunneling and the compression technologies are what worth our further development, and we are doing that busily. Thank you all very much for listening.